All right, we're going to take a high-speed journey through the evolution of the cloud. We'll start with the clunky, inefficient servers of the past and go all the way to the automated, super resilient systems that power, well, almost everything you use online today. Let's dive in.
So this is the question that trips up so many people, right? VMs, containers, Kubernetes, they sound kind of similar. They're often used together, but they solve fundamentally different problems. In this explainer, we're going to make that distinction crystal clear, one layer at a time.
To really get where we're going, we have to look at where we came from. And not that long ago, if you wanted to launch an application, you had to buy a physical server, install an operating system, and run just that one single application on it. The biggest problem? Just massive waste. Most of the time, that super powerful server was just sitting there, barely doing anything, using just a tiny fraction of its potential.
So this incredible inefficiency just couldn't last, and it led to the first major breakthrough in our story, virtual machines, or VMs. This was the first giant leap towards solving that problem of all that wasted hardware.
The big idea behind VMs is a concept called virtualization. And really, it's the art of taking one physical computer and making it act like many different computers. Each one is completely separate from the others and has no idea it's sharing. It thinks it has the whole machine all to itself.
Okay, so how is that even possible? It sounds like a magic trick. Well, the magic here, the piece of software that makes this entire thing work, is called the hypervisor.
Think of the hypervisor as a traffic cop for the computer's hardware. It sits right between the physical machine and all those virtual machines. And it carefully manages who gets how much CPU, who gets how much memory, and who gets how much storage. This makes sure one VM can't just hog all the resources or, mess with another one.
And this really gets to the key takeaway. Each VM is a complete self-contained package. It's got its own full operating system. It's like building several individual houses on one plot of land. Every single house has its own foundation, its own plumbing, its own electrical system, its own full OS. They're heavy, for sure, but they're completely isolated from each other.
So VMs solve the problem of wasted hardware. Fantastic. But they created a whole new problem. They were just too heavy. Because every single VM needed its own full operating system, they were slow to start up, they took up a ton of space, and they weren't very portable. The industry needed something lighter and a lot faster.
And this is where containers completely changed the game. Get this, instead of virtualizing the hardware, containers virtualize the operating system itself. They all share the same host OS kernel, which makes them incredibly lightweight and lets them start up in seconds, not minutes. It's a huge difference.
Let's go back to our analogy. If VMs are individual houses, then containers are apartments in a giant building. All the apartments share the building's core foundation and plumbing. That's the host operating system. But each one is a secure, isolated space for its residents, which in this case is your application.
Okay, but wait a second. This is the part that feels like magic, right? If all the containers are sharing the same OS kernel, how in the world do you keep them from messing with each other? How does an app in one container not see the files and processes of an app in the container next door?
Well, the answer isn't magic. It's actually two incredibly clever features that are built right into the Linux kernel itself: control groups, which everyone calls C groups, and namespaces.
Groups are all about the how much. They're the part of the Linux kernel that enforces resource limits. A group can basically say, hey, this container right here, it gets exactly 1 CPU core and 2 gigabytes of memory and absolutely no more. It literally builds a fence around the container's resources.
So, if C groups manage how much, then namespaces manage what you can see. Namespaces give a container its own private view of the system. It gets its own list of processes, its own network connection, its own little chunk of the file system. It's completely tricked into thinking it's the only thing running on the entire operating system. Pretty clever, huh?
Okay, so containers are amazing. They're lightweight, they're fast, they're portable. Developers absolutely love them and started creating hundreds, then thousands, then millions of them. And this created a brand new problem. How do you manage all of this at scale without going completely insane? It was a new kind of chaos.
Enter Kubernetes, the pilot of the container ship. It's what we call an orchestrator. Its entire job is to automate the management of containers at a massive scale. So if containers are the apartments in our building, Kubernetes is like the super smart automated building superintendent who makes sure everything's running perfectly, makes repairs automatically, and moves new tenants in seamlessly.
The real power of Kubernetes is all in its automation. It's not just about starting containers. It handles really complex stuff, like automated rollouts, so you can do updates with zero downtime. And if you push a bad update, it can automatically roll back to the version that worked. It even does self-healing. If a container crashes, Kubernetes just replaces it, keeping your app alive. That's the power of orchestration.
So how does it do all this? Well, Kubernetes has a brain, which we call the control plane, and it makes all the big decisions. The API server is like the front door. It's how you talk to the cluster. etcd is the cluster's memory. It stores the state of everything. The scheduler's job is to figure out which machine is the best place to put a new application. And the controller manager works non-stop to make sure reality matches what you asked for. It's the ultimate command center.
And if the control plane is the brain, then the worker nodes are the muscle. These are the actual machines that do the real work. On each and every node, there's a little agent called the kubelet that's always listening for orders from the brain. And when it gets an order, it tells the container runtime, the engine that's actually running the container, to start or stop your application.
So, we've covered VMs, containers, and orchestration. The final piece of the puzzle is understanding how these technologies aren't competitors. In fact, they're actually layers that build right on top of each other.
This really shows how it all fits together in layers. At the very bottom, you have the physical hardware. On top of that, cloud providers give you virtual machines. Then, you install Kubernetes across a whole cluster of those VMs to create your orchestration layer. And finally, at the very top, you deploy your containerized applications, and Kubernetes manages them for you.
So if you remember just one thing, let it be this. These technologies aren't fighting each other. They work together. VMs give you the foundational isolated servers. Containers give you a lightweight, portable way to package your app. And Kubernetes gives you the automation to run and manage all of it reliably at any scale.
And that's really the big story here. Each step in this revolution has been about abstraction, about hiding complexity. We hid the complexity of hardware behind VMs. We hid the complexity of the OS behind containers. And now Kubernetes is hiding the incredible complexity of managing distributed systems. Which leaves us with one final thought. What's the next layer of complexity that's about to disappear?